Good morning, everybody. I want to run today's lecture and tomorrow's lecture in reverse formation. So I've decided it works slightly better if I talk about the more general case of unequal masses today, which that just simplifies the treatment of energy. I only have to do it once, which I will do tomorrow. So lectures 3 and 4 are in some sense being interchanged. So I want to do three things this morning. I want to do a complete worked example of the theory that we did last week based on this problem. I want to derive the equations of motion for this because they make an interesting comparison with some of the things we've already done and generalise the concepts that we've been using a little bit in a helpful way. And then I will talk about the unequal mass case. So first of all, I want to look at this problem with a particular set of initial conditions, and the one I'm going to choose is starting from rest, the upper mass, particle 1 fixed, the lower mass moved. So that's the motion that I'm trying to describe, okay? And the K-matrix for that problem we just found last week was 2k minus k minus k, k. And the eigenvalues were k 3 plus or minus the square root of 5. So the eigenvalue equation looks something like this. 2k minus lambda minus k minus lambda equals naught. The C1, C2. Actually, no, I'll call them A and B. A, B equals naught. So now this problem has the golden ratio all over it. The golden ratio, for those who don't know, is 1 plus the square root of 5 over 2. It's an idea that goes back to Greek mathematics. It's a particularly harmoniously proportioned rectangle, they thought. So if the sides of the rectangle are r and 1, if we take out a square, which would be here, so there's the square, 1, so that's 1 minus r, then the rectangle that's left has the same proportions. So that means that r over 1 equals 1 over 1 minus r, or that gives us r minus r squared equals 1, which gives us that r squared equals sorry, that's silly, isn't it? That's r minus 1. That's the problem there. R minus 1. So that's r squared minus r. So r squared is 1 plus r. So that's the defining property of the golden ratio. And you can easily show that that's true here. And so the eigenvalues in this problem are therefore k into 1 plus r and 1 minus r, I think. Let me have a look at that. 3 minus root 5, 1 minus r will be so if we the initial, so the problem I'm trying to solve is kx equals d2x by t squared multiplied by m. And the initial condition is top mass not stationary, that one displaced in the positive direction by A. V of naught is naught. So we need a sort of table. Lambda omega squared equals, omega is the square root of lambda over m. C transpose C transpose x of 0. So for k 1 plus r, which of course is r squared, then omega is r root k over m. C, if we put let's factor out a k from this equation so that it becomes a bit simpler. So then we get 2 minus lambda over k. 1 minus lambda over k. So 2 minus lambda, where lambda over k is 1 plus r, is minus r. Two minus 1 minus r, we decided was minus 1 over r. So the eigenvalue is either that, or alternatively it's that. And that's the version I'm going to use, okay, R1. C transpose, so that's C transpose C is then 1 plus R squared, which is 2 plus R. C transpose X of naught is just R. The other eigenvalue is lambda is 3 minus root 5, which is over 2. Did I write that down correctly up here? No, I didn't. Sorry. I missed out the 2. 3 minus root 5 over 2, which is 2 minus r. So that's k, 2 minus r. So omega is root 2 minus r. So that's omega 1, that's omega 2, root k over m. The eigenvector is orthogonal to that one, so it'll be that. C transpose C will then be the same, 2 plus R. C transpose x of 0 will be just sorry, I said that wrong, didn't I? That one is A, and this one is minus RA. So, putting all that together, we get x of t is first mode A cos omega 1 t minus R times the eigenvector, which is R1, minus RA cos omega 2t times the eigenvector, which is 1 minus R. So it's basically, once you've got once you've got the eigenvalues and eigenvectors, it's just entirely formulaic, constructing the complete solution. And so you'll observe that here the initial displacement of the top mass is is RA minus RA, and the initial displacement of the second mass is wait a minute, stop, and there's a denominator which is 2 plus which is 2 plus R, and the initial displacement of the second mass is A minus plus R squared A, which is 2 plus R. So that's the complete solution, and that's how it works in the obvious way. So that's kind of given you a complete recipe for equal mass normal mode problems, but I wanted to just derive the equations of motion for this system because it's helpful to have the idea that normal modes are much more generic than they are, and this is not a linear motion system, this is a rotational system. And so in the first place, the elements of the vector x are not now displacements, they're angles, and the thing that I've been calling m now becomes a moment of inertia. So the equation of motion for we have two equal pendula. They each have moment of inertia I, and the centre of mass is somewhere fairly well down here, so it's down here a distance L, so the centre of mass is L from the pivot point, and the thing's got a mass M. The rotating mass around this pivot here is M. So the rotational equation of motion will be I d2 theta 1 by dx squared is the sum of the torques, and one of the torques, so if I just sketch the displaced, I'll draw it as a bar because the important point is that it's not a point mass. So somewhere down here, so there's a support here. There's the weight acting through the centre of mass there, mg, a distance L down there. So the torque is minus mg L sine theta. So that's theta 1, which I'm going to approximate in the usual way to minus mg L theta 1. So there's a minus mg L theta 1, theta 1. And similarly, for I d2 theta 2 by d t squared, we get minus mg L theta 2. And then there's the coupling spring, which gives an extra torque. So if we displace this one by the one that's closer to you, which is theta 1 by theta 1, displace this by a larger amount, theta 2, then that's introducing a torque which is a positive torque on theta 1 and a negative torque on theta 2. So that's plus, I'll call the rotational constant, I will call h. So that's torque per unit angle, like force per unit extension for a spring. So that's h theta 2 minus theta 1, and here it's minus h theta 2 minus theta 1. So what do we get after? So my vector x is now theta 1, theta 2, and my equation of motion is I d2 x by dt squared is, and this time the matrix K, we put a minus there and we put an x there. So the coefficient of theta 1 is mgl plus h, and the coefficient of theta 2 is minus h, and here it's minus h on theta 1, and it's mgl plus theta 2 there. So the K matrix, the stiffness matrix, is mgl plus h minus h minus h mgl plus h. So that's still in very similar to the equation of motion that we had, where we had the extra fixed point for this system, where the matrix had the 1, 1 and the 2, 2 elements identical. We have that again. We have mgl plus h and mgl plus h. So whenever you've got a K matrix of the form K11, K11, K12, K12, that is to say these two are the same and those two are the same, then the eigenvalue equation is K11 minus lambda, K12, K12, K11 minus lambda is 0. And the eigenvalues are lambda, K11 minus lambda squared equals K12 squared, and so lambda is K11 plus or minus K12. So in this case it's mgl, which is mgl is that mode where the coupling spring isn't doing anything. So we have, lambda 1 is mgl, omega 1 is the square root of mgl over I, and C 1 is 1, 1, because if we put K11 plus K12 in here, we get minus K12, K12, K12 minus K12, and the eigenvector in that case is 1, 1. For lambda 2, we get mgl plus h, so omega 2 is the square root of mgl plus mgl plus 2h, mgl plus 2h over I, C2 is 1 minus 1. So we can use the same nomenclature of K and X for the components of the thing, but the elements of K are no longer have the value of spring constant, they have the values of torque per unit angle, so in fact they're torques, and the elements of the vector x are no longer displacements, they are angles. In general, there is one can probably find problems for which the elements of the vector x are not all of the same kind. Some of them are, maybe some of them are displacements and some of them are angles. In that case, of course, my desire to have the eigenvectors just pure numbers will certainly not work, because the vector has to take account of the change in dimensions, the different elements of the X matrix. So if one of these was a displacement and the other was an angle, then you couldn't have these being dimensionless. However, we're not going to explore any problems which couple together angular degrees and linear degrees of freedom, so I'll just leave that to one side for the moment. Now, I'm trying to drink hot black currant because I haven't got a huge amount of voice, and there's some slight risk I won't make it to the end of the lecture. Right. So now I want to... So this is again a problem with basically the two oscillators being the same. They're not equal mass, they're equal moment of inertia. I now want to address the problem, what happens in the more general case So let's go back to example, the example we first looked at, but let's suppose, so that's to say, that example there. But let's suppose that the masses are different. So the equations of motion, the two m's now have to acquire substrate. So we have to have m d2x1 by dt squared equals, well, it doesn't change this side of the equation, so we can still write this side of the equation as minus k x. No, we can't do that. Minus 2k x1 plus k x2, and m2 d2 x2 by dt squared is k x1 minus k x2. So that's exactly the same equation of motion we had before, but these two m's are now different. So how do we accommodate that into a vector and matrix formalism? The right side of the equation can still be written kx. What about the left side of the equation? Well, what we have to do, because this row has been multiplied by m1 and this row has been multiplied by m2, we have to pre-multiply by a diagonal matrix with elements m1 there and m2 there. So if we now read across the first row of that equation, it reads m1 d2x1 dt squared is the first row of that, which is what we had here, and m2 d2x2 by dt squared is the second row of that, which is what we had here. So that's certainly doing the right thing. However, let's now substitute our general solution, x, our general normal mode solution, I should say. X is C f of t. I'm going to call this matrix here capital M. So that reads M C d2 f by dt squared equals, sorry, that's minus kx, minus kc times f of t. So again, we can divide by f because it isn't always 0, and we get 1 over f d2 f by dt squared MC equals minus KC. Now this is subtly different from the equation that we had before, because this quantity here had the m was factored into this, but the m can't now, but the m now is forming part of this product, matrix product here. So the dimensions of this, I mean, it's still the case that this side of the equation does not depend on time, and therefore this side of the equation cannot depend on time, and therefore this quantity here must be a constant. The only question is, what are we going to call that constant? Last time we called it lambda. Well, I'm going to call it lambda again, but we should point out that last time lambda was one of the eigenvalues of k, and it had the dimensions of spring constant. On this occasion, it's just obvious looking at that, this has dimensions of time to the minus 2. It's a second derivative with respect to time of f divided by f. So this has dimensions of frequency squared, not spring constant, okay, but I'll still call it lambda. Actually, I've got a suspicion in the notes I call it omega squared, so why don't I do that? So I'm going to call that constant there minus omega squared mc equals minus kc. And so we've ended up with a kind of eigenvalue equation mc. But it's got an extra matrix in it. So Kc on the eigenvector C produces matrix M times and vector C, and there's a constant here, which is in fact the eigenvalue. So I mean, I could also have called that lambda, because that, but I'm only calling it omega. In fact, I'll leave it at that. But it is essentially the eigenvalue lambda. And what's happened is that this is what's known in the mathematical trade as a generalized eigenvalue problem instead of an eigenvalue problem, and it's generalized by the inclusion of this matrix M. And it's rather important that this isn't any old matrix. This matrix M has two important properties. It's diagonal, and the elements on the diagonal are positive definite. They're not even zero, they're positive definite, okay? And that's crucial. And that means it's an appropriate form, it's an appropriate sort of matrix to go in there, because in fact what it is it's a metric. It's the other, I mean, in the notes I refer to this as an eigenvalue problem with metric. And you can prove all the same nice properties for eigenvalues and eigenvectors with regard to a metric as without. So I'll just, for example, prove one of those. So, well, first of all, how do we find the eigenvalues? So now we can take the two terms onto the same side. K minus lambda m c equals 0, and therefore det k minus lambda m equals 0, and therefore we've got in this particular example 2k minus m1 lambda minus k minus k minus m2 lambda equals 0, which gives us 2k minus m lambda k minus m lambda minus k squared equals 0, except that's m1 and that's m2. And so that's m1, m2 lambda squared minus 2k m2 plus k m1 lambda plus k squared is naught. So that's the quadratic whose roots determine the eigenvalues. And I won't pursue that any further. It's obvious what we do next. And then we can go back to the matrix equation here and find the elements of the vector in exactly the same way as we usually do. We put the stuff into the matrix. We find that the two equations now become the same equation, or the same equation multiplied by a constant, and so we can't determine the elements of C, but only their ratio. Did you look at generalized eigenvalue problems in linear algebra last term? I think I'll take that as a no. Right. So let's just... So this is not the only way of handling the problem, of course. At this stage, I could have multiplied by the inverse of this matrix to give me d2x by dt squared equals a matrix on this side times x. That matrix would then not have been symmetric. The reason for doing it this way is that we have a symmetric matrix, which means we have all the special properties that come with a symmetric matrix. And by going to an unsymmetric matrix, I can't then rely on those properties being true. This way, we stay within symmetric matrix land, and that's a convenient place to be. So let's just look at one of the special properties, which is the orthogonality. It's still the case that the eigenvalues are real. I won't give the proof for that. But let's look at the orthogonality of eigenvectors, since that's the crucial one, and it also tells us how orthogonality is now defined. Suppose we find two eigenvectors, C1 and C2, belonging to eigenvalues lambda 1 and lambda 2. That is to say, we have k C1 is m lambda 1 m C1, and k C2 is lambda 2 m C2. So let's construct the product C2 transpose k C1, and so I could achieve that by multiplying this equation here by C2 transpose, and that will give me lambda 1 C2 transpose m C1. Okay? And let's look at another way of doing that. Let's multiply this one by C1 transpose, and then take the transpose of the whole equation. So that will give me C1 transpose k C2 is lambda 2 C1 transpose m C2. So I now want to transpose that equation, and when you take the transpose of a matrix equation, you reverse the orders of the factors. So that will be C2 transpose K transpose, and this is where the fact that it's a symmetric matrix matters, because K transpose is the same as K, and then C1 equals lambda 2, and the transpose of that is C2 transpose, and then it's the transpose of M. And M is not just symmetric, it's also diagonal, but it certainly is the same as its transpose, C1. So this equation and this equation are identical apart from C2. So if I subtract them, apart from the lambdas, I get lambda 1 minus lambda 2 C2 transpose m C1 equals naught. So that came from subtracting that equation and that equation. And this side then gives 0, and the other side gave what I just wrote down. So either lambda 1 equals lambda 2, in which case for this problem C1 equals C2, or C2 transpose M C1 equals 0. So that is how orthogonality is defined. Orthogonality is defined with an M between the two vectors. And in this case, if lambda 1 equals lambda 2, then this product here becomes C1 transpose MC1. And if you think about it, that is A squared M1 plus B squared M2. And so it's a sum of squares, but the sum of squares are multiplied by coefficients M1 and M2, but the coefficients are positive definite, which I said was a requirement. And that's why it's a requirement. The norm, this is the norm of the vector, the norm is still positive definite. And therefore, it's still, this can't be 0, and so that must be 0, which in that case it is. So we have orthogonality is defined with respect to the metric. So you can't just kind of look at two vectors by sight and see that they're orthogonal, because in fact, a dot product of two vectors directly in this formalism never occurs. We only ever get orthogonality with respect to the metric. And therefore, even though we're dealing with the same K matrix, the eigenvalues are different and the eigenvectors are different. Okay? So it's still the case. It's that the eigenvalues are real and the eigenvectors are complete. And there's a sort of sketch of a proof for that in the notes. So I'll use those two properties to work out the solution. Suppose we now have some initial the general solution in that case well, we haven't actually solved, so it occurs to me, we haven't actually solved the other half of the equation, because the other half of the equation was d2f by dt squared equals minus lambda f, so which is why I was defining lambda is omega squared, because f will be fi will be, well, that's I, so ai cos omega I t plus bi sine omega I t. And so my general solution is putting all that together will be x equals C1 A1 cos omega 1t plus B1 sine omega 1t plus C2 A2 cos omega 2t. So that's the same, you can't tell just by looking at that we're in a different type of solution and a different type of problem. This bit here, the solution in terms of normal modes with arbitrary coefficients a's and b's, it looks identical to the general solution in the previous case. But if we now introduce some initial conditions, x of 0 equal x of 0 and v of 0, initial conditions. So if I put t equal to 0 in there, we get x of naught is C1 A1 plus C2 A2. So far the same, but now the orthogonality works different. How do I use the orthogonality? So in order to isolate, for example, the term C1, I have to multiply by a vector that's orthogonal to C2, and but we know that in order to do that we'll need x2 transpose m. So I'm going to multiply on the left by C2 transpose m x of naught equals C2 transpose m C1 A1 plus C2 transpose M C2 A2. And so we now, let's bracket the vector bits. So that's 0, and so A2 is C2 transpose M x of 0 divided by C2 transpose M C2. And similarly for the other one. So that's exactly the same as it was before, except the dot product here, I said every dot product has an m in it. There was a dot product in the numerator and a dot product in the denominator, and they've both acquired factors of m. So that works in as similar a way as it could do. And then if we differentiate that to find the velocity, we get C1 minus A1 sine omega 1 t plus B1, wait a minute, A1 omega 1 sine omega 1 t plus B1 omega 1 cos omega 1 t plus C2 times minus A2 omega 2 sine omega 2 t plus B2 omega 2 cos omega 2 t. And so V of naught is, this goes away, B1 omega 1 C1 plus B2 omega 2 C2. And those are the vectors. So that solves in a very similar way. We get B1 omega 1 will be C1 transpose M V of naught over C1 transpose M C1. And similarly, we can find B1 explicitly by taking the omega down there, omega 1. So the general solution is very similar in terms of initial conditions to the previous one, except that there are metric tensors in all the dot products, metrics in all the dot products. So x of t is sigma over modes C1 transpose M x of naught cos omega 1 t. These are i's. I plus 1 over omega I Ci transpose m v of naught sine omega I t, close bracket, divided by Ci transpose m C1. So if we just look briefly at the dimensions going on here, the C's are all dimensionless, so we've got a dimension of mass in the denominator, we've got an extra element of mass here, and then we've got displacement through the x of 0. So overall, the two masses cancel, the C's are dimensionless, and we've got displacement coming from the x there. Here we've got velocity divided by frequency, which is a displacement, and again we've got an extra mass which cancels with the mass in the denominator. So that's the general solution in terms of initial conditions. Let's now go back to that eigenvalue equation that I found some time ago, if I can find it. Here it is, here it is, here it is. So let's divide through by m1, m2 to give lambda squared minus 2k over m1 plus k over m2 lambda plus k over m1 k over m2 equals 0. And so lambda is k over m1 plus a half k over m2 plus or minus the square root of that thing squared, k over m1 squared plus a half k over m2 squared, and then minus AC, where k squared over m1, m2. And the effect, this term here actually cancels the cross term. The cross term between these two is twice times a half times k squared over m1, m2, which is cancelled by that. And so that square root factor becomes the square root of k squared over m1 squared plus a quarter k squared over m2 squared. And so lambda is k over m1 plus a half k over m2 plus or minus like that. So, and you'll observe that this is a sum, and that's a sum of squares, and so this is less than that, and therefore both of those are positive always, as you'd expect. And if you look at what those frequency squareds do, so this is also equal to the frequency squared omega squared, and if you look at what those do as a function of I don't know, m2 over m1. So in the equal mass case, it looks something like that, you always get 2 in the limit of very small m2, we get k1 over m1 plus or minus k over m1, which gives us 2k over m1 and 0. In the limit of vanishingly small in the limit of very large did I say that wrong? So in the limit, so this is very small m2. Very small m2 means this term is the dominant term. Sorry, that's m2. And in the limit of very large m2, in the limit of small m, when this ratio is very small, m2 is very small compared with m1. We have basically a large mass in the middle and a tiny little mass here. And so this mass here isn't really doing anything. There's a main mode with basically doing that. And what this mass does really doesn't count for anything very much. On the other hand, if this is the big mass, then basically there's a mode which is just doing that, and this mass doesn't move. And then there's a very, very slow mode where it's doing this very, very slowly because of the size of this mass. That doesn't necessarily show that terribly well because it right. So I'll come back tomorrow and talk about the energy in both the equal and the unequal mass cases.